Howdy, everybody. Hope you're doing well wherever, whenever you are. We're here for day 17 of Advent to Code 2015. So we're just trying to build up those problem solving skills, trying to do it regularly enough that I don't feel inept at it when this year's Advent to Code comes around. So that's where we're at. We're on day 17. Love to see how you solve it or your thoughts or anything like that. So just let me know in the comments, or you can I have gists of all of my solutions. um you can use that gist to I think you can like fork it and put your own solution in there, and then at least that's how it's happened in the past, and I've done that to solve it. So or done that to look at your solutions, I guess I should say. So feel free to do that. But with that, let's move on to day 17. So, no such thing as too much. The elves brought too much eggnog again, 150 liters this time. To fit it all into your refrigerator, you need to move it into smaller containers. You take an inventory of the capacity of the available containers. For example, suppose you have containers of size 20, 15, 10, 5, and 5 liters. If you need to store 25 liters, there are four ways to do it: 15 and 10, 20 in the first 5, 20 in the second 5, then 15, 5, and 5. Yeah, so like some combinations of containers won't work. Filling all containers entirely, how many different combinations of containers can exactly fit all 50 liters of eggnog? So I did get the puzzle input. I saw it was a bunch of numbers. It is very large. Well, there's only 20 of them, but that's very large when it comes to like permutations and combinations. So, yeah, like my thinking that's going on is this one's probably not a good one to try and just say, give me all the permutations. And I think there's probably a better way. There's like a fill, we can use like dynamic programming. I can't remember what they call it. It's like a fill something. But you can see 2.4 to the 18. So, uh, what is that? It's like in the quadrillions or quintillions. It's some large number. Uh, that starts to get unreasonable, right? Like if you imagine you could do a million a second, you're still in the range of 20,000 seconds or something like that to solve it. Uh, but I think we can do better. Like there's I wish I could remember. It's a dynamic programming thing, but you basically say like, you take the 20, and then you say, now given the rest, can I? I mean, it's a part of dynamic programming. You say, now given the rest of the containers and 5 liters, because I've used 20 of it to fill this, how many ways can I, can I use this one? No. Can I use this one? No. Can I use this one? Yes. Can I use this one? Yes. And so now you say, oh, with the 20, I can do these three. And then you like mark the 20 off and you say, okay, with the 15, which one can I use? And you kind of like go down the list, right? So you say, now with the 15, can I do a 10? Yes. Can I do a 5? No. Can I do a 5? No, right? But then you combine these. Anyway, I think it'll make more sense as we start doing it. You're basically um taking stuff away from the leaders and adding it to your like set of found ones. And then eventually you'll say, oh, okay, I can do this many with these ones left. Um, and then you kind of count them up. So we'll try it that way. Hopefully, I don't botch it too much. First we need to parse them. So this is a really simple parse, right? So I think we can actually just do like let containers equal input dot lines dot map parse unwrap dot collect vec usize. I'm gonna do isize because I think there's things that can like that it will go negative. Okay, so we have our containers, and then we want to return like this little helper function. So for now, I'll just call it, and we'll return our list of containers. And what else do we want? We want the size, which or the total amount of liters, which is 150. Which is how much left. How much is left? How many different combination of containers can exactly fit all 150 liters of eggnog? I think we just need these two. I could be wrong. Let's start. So pub fn, or I guess it doesn't need to be pub. So we'll get a list of isize and the remaining, which will be in isize as well. And then we'll return a count for those. So our sentinel, so our sentinel case is like if remaining equals 0, we return 1. So if we ever get to the point where there's nothing remaining in here, we know we found one and we can return it. Otherwise, we want to say like we want to pluck the first container off and then try and fill it, try and use it with the rest, I think. So we'll say like if containers we should do an else if containers dot len is less than 1, return 0. So we know there's at least one container. So we'll say if that is less than or equal to remaining, then we can return the count of what? E1 helper containers 1 remaining minus containers 0. I want to test this on the small one because we know that works. Because I feel like there's one step in this that I'm missing. Zero. Wah, wah. So we have a list of containers. Let's just make sure that's right. $20, $15, $10, $5, $5. Okay, so we have a list of containers. We have what's remaining. If we ever have remaining equals 0, we know we found one solution. Else, if we've run out of containers, oh, I need to loop. So we try and pick this container. It should be like this. For container and containers. Is it like that? Still none. So if the container size is less than or equal to the remaining. Oh, I need to keep track of the count of each of these. So it's found 3. What am I missing? Maybe that? That seems like it would make it worse. Oh, it's not container 0. It's container. Okay, there we go. Yeah, I think this is right. So, like, just to be clear, what's happening is we're kind of doing this dynamic programming approach, right? As we're saying, okay, give me a list of containers and how much we have, how much we want to, how much we have remaining to fill. If I've ever gotten to the point where I have none remaining, then I know I've found one solution. If I ever gotten to the point where there's no containers left, but there's still some remaining, then I haven't. Then this path doesn't lead to a solution, so I should return 0. And then what I'm going to do is go through each of the containers, see if I can use that container, right? Because I have to fill it exactly. So I should never do like if it was ever greater, then I wouldn't want to use it. So I want to eliminate those. Then I can say, okay, well, call the P1 helper on the subset, right? So use the rest of the array and the remaining minus that container and call it recursively. And so increment my count for all of those that I find and then sum them up. So you do this like recursive process. And hopefully that should solve the problem for the regular day. And we can do some analysis on it after too. I think will be interesting. So 150. Hopefully this doesn't take like a year to run. It does not. Hopefully it's the right answer. It is. Okay, good. So just to be clear, before we start on part 2, like why is this better than just brute forcing it is because you're able to like skip a lot of solutions with this method, right? Is you're able to say, oh, there's some containers where it's going to be too big, or there's some paths where I'll have used all the containers and I won't have been able to solve it, right? And so you're able to like prune down the number of checks you do. Maybe there's what doesn't like about this? So this will give us the count of like the calls that were made. You see, I only made 55,000, whereas if I tried all the permutations, it would have been quadrillions, right? And again, it's probably more than that because you're doing a combination of like of all the permutations, so it could be like really large, right? You're basically how do I say this? It's not permutations, it's combinations. And you have to do multiple sizes because you don't know what they are. So it almost is like permutations. Like you'd have to give me all the combinations of size 1, then size 2, then size 3, and so on. Hold on a second. Do you guys hear that? Hold on. Okay, so that's hopefully this makes sense. This is one of the cool things of like recursion and dynamic programming is you're just breaking the problem into smaller pieces, right? If you're asking yourself, oh, well, how do I fill the 150 liters remaining of these 5 things? It can be difficult. But if you just say, okay, well, what if I use the 20 and then ask myself, given the rest of the 4, how many ways can I fill, the remaining 5 or whatever? And you just do that recursively over and over again, and it solves the problem pretty easy, right? So not too bad. I'm going to get rid of this calls thing though. That was just like an example to kind of give you an idea of how it simplifies things. But there you go. There's part 1. Not too shabby. So part 2. Oops, I didn't do that right. Part 2. While playing with all the containers in the kitchen, another load of eggnog arrives. The shipping and receiving department is requesting as many containers as you can spare. Find the minimum number of containers that can exactly fit all 150 liters of eggnog. How many different ways can you fill that number of containers and still hold exactly 150 liters? In the example above, the minimum number of containers was 2. There were 3 ways to use that many containers, and so the answer would be 3. Yeah, so these ones are the right size. So this one's different in that we want to now track how many containers we've used. So we're going to still do the same problem, but we're going to track how many containers we've used and then only increment the count if the containers used is the min. I think that's right. So we're going to have a P2 helper as well. But now we want to track the min size and the min count. And the used. So we'll say let mute min size equals u size max. Let mute min count equals 0. Let mute used equals vec. We'll use it in a second. But we want, so we want to pass mute min size, mute min count, and mute used. This is actually going to be different too, because now we're just going to return min count. And that's going to be an I size. And min are used. So I'm not going to return values anymore. We're going to track our mins like right here. So we're going to say if remaining equals 0. So if we've gotten to the 0 and min size is equal to used.lane. Why doesn't it like that? Oh, I'm doing, they should be U sizes. So if the remaining is 0 and the min size is this, then I should do min count plus 1. I'm going to do this for this. Return. But we'll also do else if remaining equals 0 and min size is greater than use.len. So in this case, we now want the min count to be 1, and we want the min size to be use.len. And we can return here too. Else if containers.len. Like that. So we say, and these are in a weird order, we can rearrange them later, but we say, hey, if we found it, if we've filled it up and we're at the min size, then we can increase. If we found a smaller one, now we have a new min size and our min count is now 1, and we return that. Otherwise, if we've run out of the containers, then we're done with this thing and we can finish. And so now for this, we don't need to keep track of a count anymore. And we just need to call this P2 helper on each of the containers that can fill it. But we want to add like use.push, used.push container. And we want to do use.pop to remove that container. And then here, we need to include the min size, min count, and used. Like that. I think that's right. So again, we're still doing dynamic programming. We've just changed how we're tracking stuff and which values we're interested in. But I want to do it against the test. So 25 for those, right? Four and 3, those are the numbers I was looking for. So unless I did something really bad, this should work. This. 17? So, oh, okay, that's the right answer. Okay, not too bad. This one is a little bit harder because you at least than any of the other days we've had so far. And why is that? Because it's because of the how do I say this? So this one was a little bit harder because the problem couldn't just be solved with brute force. It feels like up until this day, all of the problems could basically be solved with brute force. You're just like, here's some kind of constraint or some kind of filter I need to use, and I'm going to run it until I get through that filter. But this one actually required a little bit of effort, right? In saying, oh, I need to find some way to like pick the right sizes that equal them. And again, this is, I think you could kind of get there without like the recursion thing, but the dynamic programming way is the kind of the way to do it, is like take this one and try it or remove it from the remaining list and then see how many you can make with the rest. And part 2 just changes in that you're saying, I'm going to do that same thing, but now I just need to track what the min is and how do I get to the min the fastest. Or sorry, how many of the men there are, not the fastest. How many of the men there are. And so that's what changes in part 2. And that's why I'm tracking these things, right? I want the minimum size, I want the minimum count, like how many I've found of that minimum size, and then how many I've used in this like dynamic programming recursion path kind of thing. So the logic looks a little bit different. Let's see. Yeah, I mean, you could technically remove this and just add it in there. But this feels readable. I think the part 2 is okay as well. Min size, min count used. Yeah, I do want to fix this right here. Feels more natural to do it in this order. So like this case is we found a smaller min. And then this case is we another min. And in this case is no more to try. I guess technically the no more to try for this one is okay because you're just enumerating through all of them. It's actually okay to try on this one too. So we could, like, as an optimization, you could do this. And that, and presumably you get the same numbers. Yeah. Like, so why is that, right? If there's no containers, this for loop's never going to run. And it happens to be the same case up here, right? You're keeping track of that count. And if there's none in the list, it happens to be 0. This could also be turned into something functional, right? So you could say containers iter enumerate dot filter. Oh, it's like this though. Oh, I need a double D reference here. I think that gives you the same answer. I don't know. Does that way feel better? Possibly. So what's different? I mean, you're literally doing the same thing logically, but now you're using filter and map and then summing over those. And again, obviously, if there's no items in the container, then it's going to be 0. This one, you could do it as well. It would be like a for each, though. So I mean, I can show you how it would look, but this feels pretty reasonable. So if it were me, I probably wouldn't change this one. But like if you were, let's say you wanted to do it in a functional way, we'd have the same filter right here. Where was that? Iter enumerate filter. Like that. Yeah. It's funny that it doesn't. Okay, there we go. It's probably because it wasn't formatting, but it's probably because I had formatted it weird myself, and so I thought I wanted to keep it. But okay, what do? We iter enumerate filter the same way we did before, but then instead of calling map and sum, we're just calling for each on each of them, and the for each is we add it to our used list, call it recursively, and then remove it from our used list. Okay. I don't know. Tell me what you think. How does it look code wise? Does the idea make sense? We can talk about dynamic programming more. I'm sure there's other problems and other days where it will come up. So, but if you have any specific questions about why choose this way or why not, I'd be happy to try and answer them. Again, that's not. I'm not amazing at any of this stuff, but um, happy to help where I can. So there you go. There is day 17 in the bag. Thanks everybody, and we'll talk to you next time.